What is this Netflix price? In October 2006, Netflix said that, look, I got something called Sign Match. That's the internal recommendation engine that Netflix was using. And it gave me certain kind of RMSE value. But I'm wondering if I can do better. For example, can I improve this by, say, 10%? You may say, well, 10% is not a big improvement, isn't it? Well, first of all, this Sign Match was not a stupid algorithm. And second, even a few percent improvement in the RMSE can change the order of the recommended movie and therefore the effect on customer satisfaction, inventory control, and so on. So it said that from 1996 to 1999 to 2006, I got 7 years of records of ratings by different users on different movies. And I'll make available about 100 million of these ratings that come from 480,000 users on 17,770 movies. Okay. So on average, each movie was rated by more than 5,000 users, and each user rated more than 200 movies. Now you can see that this is a huge data set, and it's all real data. Of course, it's anonymized, and there was some controversy on how well was the privacy protected. But that's outside the scope today. So it's big data. It's also sparse data. Okay. Because only about 1% of the total number of possible rating were actually known. Okay. If you multiply the number of movies with the number of users, you actually see this is actually a small number. And furthermore, it is skewed data. The average number of users per movie and movies per user, it's kind of big, reasonable numbers, but some users actually rated a lot of movies. One user actually rated almost every single movie out there. And some users rate very few movies, just several of them. And whatever recommendation engine you use has to work for all movies and all users. So how do we deal with the big, sparse, and skewed data? And that's the challenge from this Netflix price, to get to 10% improvement over the Sign Match RMSE. Now this was a huge attraction already. And on top of that, Netflix also offered $1 million US to whichever team or person that could get to 10% first. So this was the famous Netflix price. It's open to all countries and people except just a couple. It's online. Okay, you don't have to show up in person, and it's international. Clearly, both the $1 million and perhaps more importantly, the huge data set made available were very attractive to the machine learning, data mining, information retrieval research community. So we're going to take a quick look at the data set that's involved here. The entire data set, which is a little over 100 million entries of RUIs, were divided into 4 parts: the training set, the probe set, the quiz set, and the test set. You may say, why make it so complicated? For example, why don't we just make it into 2 sets, the training set and the test set? Well, it turns out this is a pretty smart arrangement. Okay. The training and probe set were made public, and they're just big enough that it becomes very interesting. It's small enough they can fit into a normal laptop in 2006. And then the quiz and test set. These data were hidden. Okay. Only Netflix have the ground truth. The competitors in the price did not have access to these actual data. So as far as our competitors, say you and I form a team, as far as we're concerned, we have access to training data, which is almost 100 million, plus 1.4 million of probe data. Since we have access to this data, we can just hide it as ground truth, train our algorithm, and then look at the recommendation accuracy on the probe set. It turns out that the probe set size and the statistical characteristics in terms of distribution of movie and user are very similar to the quiz set and the test set, which we don't know. So we can use this to test our methods as frequently as we want, many times a day. But then the actual competition result is not determined by this. It is determined by some unknown to us data known to Netflix. So we can submit our algorithm up to 1 time a day to the quiz set. Why a limitation? Because if we submit too many times, say every 50 seconds, we may have enough hint on the actual underlying data and reverse engineer the ground truth. Then that wouldn't be useful for Netflix. And once somebody can hit 10% improvement over SciMatch RMSE on the quiz set, it enters into the final call phase, and then the final result will be based on your performance in terms of RMSE on the test set. The leading teams are shown on the website. Now, I think the website is still alive. You can just Google Netflix prize based on their performance of RMSE on the quiz set. So basically, you use training set to train, probe set to test yourself, quiz set to test on a regular basis if you want, but not too frequently, and then the eventual result is on the test set. And you wonder, this 10% improvement, why not say 11%? Why not 9%? Well, I don't know how Netflix decided on 10 is a good round number, but had it been 11%, it would have been a lot more challenging. So happens for this metric and this set of data, both the training and the test set, getting to 11% would have been extremely difficult, and getting to 9% would have been a little too easy. It's a good pick, 10% too, in hindsight. So what happened in the competition? It's a very interesting scientific story. We just briefly present some highlights. First of all, very soon, within a week, okay, somebody already was able to actually beat SciMatch. Okay, but you need to beat by 10%. So we have to go from 0.9514 up to 4-digit of accuracy of RMSE on the quiz set. Remember, the test set is reserved for the final phase. So 10% beating by a tiny bit on the quiz set in terms of RMSE over SciMatch was achievable within 1 week. Now I have to push this down by 10% all the way to 0.8553. Now you may wonder, oh, these are very small numbers, less than 1, and 10% of that is very small. Well, actually, don't forget, this whole thing is on the scale of 1 up to 5 stars. Okay, so 1 is actually a pretty big deviation. For example, if you see a movie recommended with 4 and 5 star, 4.5 star versus 3.5 star, that actually clearly shows a big difference. All right, and then in almost 1 year's time, by September 2007 now, there's a team called Bellcore that made a 8.26% improvement over SciMatch. Very good. Seems that 10% would be imminently achievable, but that turned out not to be the case. The first place changed hands a few times until in the last 1 hour before the first year of competition ended. This same team retained the leading position with 8.43% improvement, and that gave them $50,000 US of an annual progress prize for leading the chart, even though it didn't succeed in getting 10%. And then what happens from 2007-2008 is the teams start to merge. If a mom and pop shop back then are able to be somewhere on the chart, it becomes very difficult because the smart teams merge together so that they can share their secret. In particular, Bellcore and Big Chaos, another team, merged, and this team won the 2008 Progress Prize in October of that year. And at that point, this RMSE gets down to 0.8616. And then emerged again with a team called Pragmatic Theory. So now these three teams become one team. It's called Balcour's Pragmatic Chaos. So grab one word from each of the original three composite teams. And in June 2009, almost 3 years into the competition, this merged team became the first one to achieve more than 10% improvement. Okay. In fact, it got 10.06% on the quiz set in terms of RMSE over SciMatch benchmark. At that point, the competition entered into the final last call phase. All the team got 30 days to make the final submissions. At the end of that time, two teams actually beat SciMatch by more than 10%. Okay. One team is this Balcour Pragmatic Chaos, which got an RMSE of 0.8554. Okay. The other is called the Ensemble, got 0.8553. Actually, that's slightly better. But remember, that's on the quiz set. The final prize will be determined on their performance on the test set that no one has seen yet, or no one has been using yet. And here's the grand finale. Actually, all of them, both of them, received 0.8567 as the RMSE. The same performance up to fourth digit. That's what the last digit that counts. So, who's going to win? Well, determined by who submitted the final solution earlier. It turns out Balcour's Pragmatic Chaos submitted their algorithm 20 minutes before the Ensemble. So, because they both achieved the same performance by RMSE on the test set, it comes down to the submission time, and Balcour Pragmatic Chaos won the competition with a differential of 20 minutes in this wonderful almost 3 year scientific quest. That's the grand finale. So you must be wondering, what did Balcour Pragmatic Chaos use to achieve this milestone and receive the prize? Well, you can actually go online and see three documents, three PDFs, okay, where you can read all the algorithm details. As part of the competition deal, you have to release your public information and allow Netflix to use it or its variant. So this is all public information at this point. Except if you go through that, you see it's just a bag of many tricks and thousands of parameters fine-tuned based on the training data. If you want to get to the gist of the key ideas, it actually will take much less time, especially if you're only interested in getting to about 8 to 9% improvement. That's what we're going to target in the next remaining part of this lecture. If you want to get to exactly a little above 10%, then it would take many more tricks. So our focus to how to get you to 8 to 9%, and what are the key ideas behind that. So here is a pictorial illustration of the problem. The problem is that you've got many users, you've got many movies, and you can put them into a matrix or table. You can also think of this as a bipartite graph, with the user nodes on the left, movies nodes on the right, and it's bipartite because only users and movies are paired up, and you can give weights to these links, 1 up to 5. So there are many possible angles. First, we're going to view this as a table. Now, in this table actually is a little misleading because A is too small. There are only 48 possible entries. Okay, whereas actually we can have around 10 billion possible entries in the actual Netflix prize. It's also very dense. You can see that about half of the cells are actually filled with actual rating data. It's a lot sparser in the actual Netflix price. So the size and the sparsity are actually not accurate. But it suffices to conceptually illustrate what the problem is. You're given these data points, which are 1 up to 5 integers, and whatever is the blank means that this user has not rated this movie. She might have watched the movie or not, but there's no rating recorded. And you see 4 question marks. These are basically entries where Netflix knows the ground truth, but you and I, as teams entering into the prize competition, we do not. Or maybe we do, but we have to reserve it as the probe set. So in any case, when we train the data, we use the data shown here, and then when we test, or when Netflix tests, then they can use these hidden ground truth. If you just stare at this particular table here, you say, well, how do I predict these 4 entries? Maybe I would say, just look at this movie, okay? If this movie is got a lot of high rating, just give it high rating, like 5.5. Oh, maybe this is 5.2. This is 4.5. Another good movie, make it 4.5. Okay, this one's 2, 3, 4. That's a tough call. Maybe I'll look at this row here. Okay, I'm trying to predict how would user 5 like movie 3, but user 5 seems to give 3 all the time. Maybe I should also give 3 here. What about this entry? The movie 7 gets 1, 3, and 4. It's kind of diverse. And this user actually gave 2 and 4. So it's really hard to say what this might be. Okay, it could be 1, 2, 3, 4, 5. I don't know, maybe just give an average. Whatever is the average of all the entries here. Let's say the average is 3.5. All right, 3.5. It sounds a little like filling out a table in the Sudoku. Well, in what we just talked about, we actually touched upon a few intuitions. One is that certain movies are, in general, better made than certain other movies. And certain users are very strict graders or very loose graders. Okay, we have to take into account those things. We can also, when there's no other help, just give up and say, take the average of the whole table as the prediction. That's a very lazy predictor. So there's some intuitive understanding just emerging, but none of this is good enough to get you 8%. Not even close. You have to think a little harder than that. Okay. But in what we just talked about, we actually have touched upon what's so-called content-based filtering. In other words, just look at an individual column or row. Column corresponds to movie. Let's say individual column. Do not worry about what the other columns show. And this is similar in a crude analogy to the Google, if Google were computing a relevance score. But if you want to do importance score by looking at the connectivity pattern among the web page, or in this case, what the other movies showing tell about this movie, then you need to go to from content-based to collaborative filtering. You say, why do I care about what the other movies are like? Because maybe certain movies are liked by a particular user. Okay? And as far as that user is concerned, maybe these two movies are very similar. And therefore, I would be able to say these two are neighbor movies. Okay? So if some user likes this movie, maybe she'll like this movie too. They're basically defining a neighborhood relationship between movies. Now, we could also do a neighborhood relationship construction for the users. If certain users from the different existing entries show their tastes are very similar, maybe then if user 3 likes a movie, user 4, even though she hasn't watched the movie, will like it too. This actually is what we intuitively do a lot of times. There's another idea, which is a little more involved, and we'll postpone it to advanced material part of the video is to say that maybe there are some kind of feature sets about these movies. For example, is this a romantic movie or action movie, a thriller movie, a sci-fi movie? Is it long? Is it short? And so on. And these feature sets is a much smaller set than the set of possible movies. There might be 20,000 movies, but only about, say, 20 different genres. And I will try to extract the underlying reason why certain movies liked or disliked by some people. And these two are the two key distinct approaches of collaborative filtering: the neighborhood method and what's called the latent factor method. These latent factors are these feature set entries. We will focus on neighborhood method and then reserve latent factor method for the advanced materials. As we just mentioned, it's a large and sparse data. That's the big challenge. One solution is just look at each row and each column in isolation. It's called content-based filter. The other is look at the entire table. It's called collaborative filtering. Collaborative among the users and movies, I guess. And this is just like this one is a centralized computation. So we don't need distributed computation. And within collaborative filtering, there are two main flavors. It turns out these two are also interestingly connected, but we will skip that. Is in the textbook and advanced material. One is neighborhood method, the other is latent factor method. Along this way of going to neighborhood method, we'll take a couple of detours. One is going into a particular optimization problem called the least squares. It's one of the most frequently used optimization problem in many diverse fields, from control of airplanes to your remote, from how light bulbs are controlled on the factory floor to a lot of supply chains. It is used in finance and economic modeling. It is used in many communication systems. It is a hugely useful optimization problem. And it is a special case of something called convex optimization. So we will take about a 5-minute detour into defining a convex optimization, because this will be a recurring theme. We'll see this a few times later in the course. And we will actually not really have time to take a detour of two very important ideas to win, say, the first year progress prize. One is implicit feedback. If somebody have not watched or have watched a certain movie, that is also useful information, not just the explicit rating. And the timestamp, TUI, is also important. First, movies come in out of fashions over that period of 7 years. And second, different users also may have different moods on different days. There's a batch processing effect. If this user decide to rate the last 10 movies she watched on Netflix on the same day, those 10 ratings tend to have a different statistical distribution than if they were entered right after watching each movie on different days. Incorporating both implicit feedback and temporal dynamics would be important for you to get to, say, 8.5% improvement over sign match. But we will not have time to go through these. So our focus right now will be on the methodology of collaborative filtering in the neighborhood method.